Welcome back to my channel. Today, we're diving into an exciting topic, using LSTM networks for physical system modeling in Simulink. If you're into machine learning and dynamic system simulation, this one's for you. Let's get started. In this video, I will cover the following topics. Introduction. This example shows how to create a reduced order model, ROM, to replace a Simscape component in a Simulink model by training a long short-term memory, LSTM, neural network. A ROM, reduced order model, is a surrogate for a physical model that allows you to reduce the computation required without compromising the accuracy of the original physical model. For workflows that require heavy computations, such as design exploration, you can use the ROM, reduced order model, in place of the original physical system. While there is a variety of techniques for building a ROM, reduced order model, this example builds an LSTM ROM, a type of ROM that leverages an LSTM network and uses it in a Simulink model as part of a deep learning stateful predict block. This diagram shows the replacement of a physical component with an LSTM ROM subcomponent in a Simulink model. The trained LSTM in the ROM, reduced order model, takes the B, base signal, and F, follower signals of the load shaft and the control pressure as input and predicts the next value of the B and F signals of the load shaft. After the model is trained, the example creates an LSTM ROM component and replaces the physical component in the Simulink model with it. Training the LSTM network for an LSTM ROM, reduced order model, is a computationally intensive task and can take a long time to run. To speed up the example skips training and loads a pre-trained version of the network. To instead train the network, set the doTraining variable to true. doTraining equals false. Generate training data. Generate the training data using the Simulink model EX_SDL_flexible_shaft attached to this example as a supporting file. This Simulink model simulates a flexible shaft. It has two flexible aluminum shafts modeled using a lumped parameter approach, the motor shaft, consisting of 20 segments, and the load shaft, consisting of 5 segments. Both shafts contain inertias, damping, and stiff torsional springs. At the start of the simulation, the clutch is unlocked and the driven shaft is free. The initial velocity of the motor shaft is set to 200 radian per second and the system starts at steady state. The model uses the pressure applied on the clutch as a control parameter to determine the dynamics of the model. The Simulink model outputs for values: 1 base, B, signal of the load shaft; 2 follower, F, signal of the load shaft; 3 control pressure. For F signal of the motor shaft. The first 3 states are used to train the LSTM ROM, reduced order model. The fourth state is used for evaluating the accuracy of the trained model. The Simulink model depends on the workspace variables stop time and time interval, which specify the final time step and the interval between output time steps of the simulation, respectively. The initial time step of the simulation is 0. Specify a stop time of 0.2 and a time interval of 5 by 10 power minus 5. Stop time equals 0.2. Time interval equals 5e power minus 5. The pressure block of the model depends on the workspace variable max pressure, which defines the value of the maximum pressure applied on the clutch. Run the model for 20 different equally spaced values of max pressure between 10 power 5 and 10 power 6. Collect the output data in the cell array data, where each element corresponds to a time series observation computed with the specified pressure profile, as shown in this code. Then we can extract the time steps of the simulations. And then plot the control pressures of the first 5 simulations as shown in figure. As shown in this figure, model dynamics are plotted: the B and F signals of the load shaft and the F signal of the motor shaft of one of the simulations. Prepare data for training. When you train an LSTM with very long sequences, the accumulation of the gradients computed for each time step can lead to vanishing gradients and cause the training process to converge to a suboptimal result. To prevent the gradients from vanishing, downsample the training data so that the sequences are much shorter without losing too much of the information. To downsample the data, specify a sample time that is larger than the sample time of the training data. When you use the LSTM network in a stateful predict block, you must specify the same value in the sample time parameter. Specify a sample time of 10 power minus 3. Sample time equals 1 e power minus 3. Downsample the training data by extracting time steps with a fixed interval given by the sample time divided by the time interval of the simulation by using the code shown in this slide. Partition the training data evenly into training and test partitions using the training partitions function attached to this example as a supporting file, and the script is shown here. Extract the predictors and targets from the training data. The predictors are the B and F signals of the load shaft and the control pressure. The targets are the B and F signals of the load shaft shifted by one time step. The predictors correspond to the first 3 channels of data train. The targets correspond to the first 2 channels of each element of data train shifted by one time step, and the code is shown here. Define network architecture. Define the following LSTM network, which predicts the next B and F signal values. For sequence input, specify a sequence input layer with an input size matching the number of inputs. Normalize the inputs by rescaling them to have values between 0 and 1. To learn interactions between the input features, include a fully connected layer with an output size of 200 followed by a ReLU layer. To learn long-term dependencies in the sequence data, include 2 LSTM layers with 200 hidden units followed by a ReLU layer. To output predictions of the correct size, include a fully connected layer with a size matching the number of responses. To train the network for regression, include a regression layer, and code is as shown here. Specify training options. Specify the training options. Train a network using the Adam solver for 3 into 10 power for epochs. To prevent the gradients from exploding, clip the gradients with a threshold of 1. To improve training, schedule a piecewise decreasing learning rate factor. Use an initial learning rate of 5 into 10 power minus 3 and decrease the rate by a factor of 0.6 every 10 power for iterations. Display the training progress in a plot and suppress verbose output. Train on a GPU. The train network function, by default, trains on an available GPU, and code is as shown here. Train LSTM network. Train the LSTM network using the train network function. To use the LSTM network in a Simulink model, save the network in a MAT file. Training the LSTM network for an LSTM ROM is a computationally intensive task and can take a long time to run. To speed up the example skips training and loads a pre-trained version of the network. To instead train the network, set the doTraining variable to true and script as shown here. Training progress RMSE and loss plots and parameters as shown here. Use LSTM ROM in Simulink model. Create the following Simulink subcomponent, which outputs the predicted B and F signals of the load shaft using a trained LSTM network. The block uses the predictions for the next time step through a feedback loop. In the stateful predict block, set the file path parameter to the location of the saved trained network and specify the same sample time used for generating the training data. Use the same sample time in the rate transition block connected to the stateful predict block input and the unit delay block. Replace the load shaft in the original Simulink model with the LSTM ROM subcomponent. The resulting model is saved in ex_SDL_flexible_shaft_LSTM. Test model. Evaluate the model accuracy using the held-out test data set. To test the accuracy of the full model, not just the LSTM network, compare the outputs with the simulated F signals of the motor shaft generated by the original Simulink model. Extract the targets from the test data. The test targets are simulated F signals of the motor shaft using the original model, shifted by one time step, and the code as shown here. We can visualize the time step predictions in a scatter plot and the prediction errors in a histogram plot as shown here. Simulate using new data. Run the model with a previously unseen maximum pressure value of 2.7 into 10 power 5 PA. And visualize the predicted F signal in a plot as shown here. Conclusion. In this video, we explored physical system modeling using an LSTM network in Simulink. The subtopics covered include: generate training data, prepare data for training, define network architecture, specify training options, train LSTM network, use LSTM ROM, reduced order model, in Simulink model, test model, and simulate using new data. This content is sourced from MATLAB Deep Learning Toolbox User Guide. Thank you and meet you in next video.